Have you ever really stopped to think about how we turn simple heat into useful work? I mean, it's everywhere, from the engine in your car to these massive power plants that light up our cities. It's a process that basically powers our entire world. But behind it all, there's a much deeper question. Just how good can we get at it? What's the absolute theoretical limit for efficiency?
So let's dive right into that, because this isn't just some engineering puzzle. We're talking about the fundamental laws of physics here. It turns out there actually is a hard and fast rule, a kind of universal speed limit for any heat engine. And to really get it, we need to take a trip back in time, almost 200 years ago. Our story starts back in the early 19th century. Picture the Industrial Revolution in full swing. Steam power is changing the world. And in the midst of all this, a brilliant French engineer got obsessed with a really unique idea. He wasn't trying to build a slightly better engine. He was trying to imagine the absolute best engine.
And what's so cool about this guy, Carnot, is his approach. He didn't grab a wrench and start tinkering with gears and pistons. Nope, he did it all in his head. It was a pure thought experiment. He wanted to figure out the ideal, the perfect cycle an engine could possibly follow to squeeze every last drop of useful work out of a given amount of heat.
Okay, so before we can really unpack Carnot's perfect blueprint, we have to get our heads around a core concept that every single engine runs on. It's called a thermodynamic cycle.
Right, so here's the deal. For an engine to just keep running and running, the stuff inside it, the working fluid, like steam or air, it has to go through a whole series of changes. We're talking pressure, volume, temperature, the whole shebang. And then, this is the crucial part, it has to return exactly to where it started, ready to go all over again. It has to be a closed loop.
Now, these cycles really come in two main flavors. We're going to be focused on power cycles. Those are the ones that actually produce work, like in a car engine or a power plant. The flip side of that coin is refrigeration cycles. They use work to move heat around. That's your fridge or your AC. So, same basic principles, just running in opposite directions.
To make this a little less abstract, just think about a classic steam power plant. You take water, you heat it up in a boiler to make high-pressure steam. That steam then spins a turbine to generate power. After that, it's cooled back down into water in a condenser. And finally, a pump sends it right back to the boiler to start the whole process over. That's a real-world thermodynamic cycle right there. Okay, now that we've got the basics down, let's get back to Carnot and his masterpiece. We're talking about the theoretical blueprint for the most efficient engine cycle you can possibly imagine. And its perfection all hinges on one beautiful, but totally ideal concept.
This right here, this is the secret sauce. A reversible process is so perfectly executed that you could run it backwards and everything, the system, the universe, all of it would return to its exact starting point without leaving a single trace. Think of a frictionless pendulum swinging in a perfect vacuum forever. In the real world, of course, things like friction and heat loss make this completely impossible. But in the world of pure theory, it is absolutely key.
And this was Carnot's genius. He basically constructed his entire theoretical engine out of 4 of these perfectly reversible steps. By completely eliminating all those messy real-world problems like friction, he was able to isolate the absolute maximum potential of a heat engine. So what does this perfect cycle actually look like? Let's walk through the 4 elegant steps that make up Carnot's ideal engine. It's really like a beautiful dance between expansion and compression. The cycle is made up of just 2 kinds of processes. You have 2 steps that happen at a constant temperature. We call those isothermal. And you have 2 other steps where no heat is transferred in or out at all. We call those adiabatic. Let's see how these 4 pieces fit together to make the whole thing work. So, step 1. We start at the top. The engine takes in heat from a hot source, like a boiler. This energy causes a gas inside to expand and push on a piston, which is how it does work. The key here is that this all happens at a perfectly constant high temperature. Next up, step 2. We completely insulate the system so no more heat can get in. The gas keeps expanding because of its own momentum, doing even more work for us. But since it's expanding without any incoming energy, it has to use its own internal energy, which causes it to cool down a lot, dropping from that high temperature to a new low temperature. All right, now we're on the return trip. For step 3, we put the engine in contact with something cold, a cold sink, like a condenser. Now, an external force compresses the gas, and as it gets squeezed, it releases waste heat into that cold sink, all while staying at that constant low temperature.
And finally, step 4, we insulate the system again. We keep compressing the gas, and because that heat has nowhere to escape, the gas's temperature shoots right back up to the original high temperature. And just like that, the gas is back in its exact starting state, ready to begin the cycle all over again. The loop is closed.
Okay, that all sounds incredibly elegant, doesn't it? Almost perfect. Which, of course, leads to a very, very important question. If this thing is the best, why aren't we actually using it? Well, this is where beautiful theory collides head-on with messy reality. The very things that make the Carnot cycle so perfectly efficient on paper are the exact same things that make it practically impossible to build. Let me give you a few examples. In that steam expansion step, you'd get so much moisture in the system that it would literally destroy the turbine blades. And trying to compress a wet, sloshy mix of liquid and vapor, well, that's a complete engineering nightmare. But the biggest deal breaker of all is that those perfectly slow, frictionless, reversible processes, they just don't exist in the real world, period. So, if we can't build it, was it all just a pointless thought experiment?
Oh, absolutely not. Its true value isn't as a blueprint, but is something way more important.
Carnot himself gave us the answer. His work revealed the single most important factor for any engine's efficiency, the temperature difference between the hot source and the cold sink. The bigger that gap, the higher the potential efficiency. That's the golden rule he discovered. And that right there is the key takeaway. The Carnot cycle isn't meant to be a blueprint. It's a benchmark. It's the ultimate yardstick. It's like the 100% on a test that no real engine can ever actually reach. But it's the standard every engineer strives to get closer to. It tells us the theoretical best we can do for any given temperatures so we can measure how well our real-world engines are actually performing. And that brings us right back to today. Carnot gave us the destination on the map, that point of perfect efficiency. The quest for engineers ever since has been to figure out how to navigate the messy, imperfect real world to get as close to that ideal destination as possible. And believe me, that chase is still very much on.